Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to evaluating definite integrals using the properties we just covered in the previous video. So this is just a continuation of an introduction to definite integrals, and we're going to go ahead and evaluate as much as we can using those properties that we just talked about. In fact, let me hop back just to show you all the properties are right there. So let's go ahead and jump in and use some of these. And this problem specifically is going to use actually a few other details. So we're going to evaluate this. This is a little bit of using the properties and using limits. So we happen to know that this can be written as the integral, the definite integral from 1 to 8 of x squared minus dx. Don't forget that dx, which I almost didn't write in there. You should always write that. Minus 4, it's supposed to be a 4, times the integral from 1 to 8 of x dx plus the integral from 1 to 8 of 4, again, dx. Now, it turns out that a few of these things you can, a couple of these things actually, you can use properties with. One specifically, and the other you can use a little bit of geometry. So let's start here. This is the integral, the definite integral of a constant. And you should always try to think geometrically. And in fact, I have an entire video dedicated to a best practice thinking geometrically when working with integrals, because you want to speed up your computation. And if you think about this function right here, just the function 4, I'm not talking about x squared minus 4x plus 4. I'm just talking about the plus 4. If you think about that, from x equals 1 to 8, the function y equals 4 looks like that. And notice that's a nice rectangle. So this can be written as the area underneath the curve 4 from 1 to 8, or in other words, it's 4 times 8 minus 1, or 4 times 7, which is 28. So that's the area of this block. 4 times 7, which is 28. So that will speed up our computations quite a bit here. 1 to 8 of x squared dx minus 4 integral 1 to 8 of x dx. And then we have that plus 28 on the back end. And I'll write that. Actually, I'll go ahead and write plus 28 right now. But what else can we do to really speed up computations? Again, think geometrically. So if you look at this integral right here, not the negative 4 times it, just look at the integral, the definite integral from 1 to 8 of x dx. Could you graph that easily? Well, answer that, I hope, is yes. Y equals x looks like this. And we want to find the area underneath y equals x from x equals 1 to x equals 8. Could you find that area of that trapezoid by hand? And the answer to that is yes, you can. You totally can do that. If you don't remember the area of a trapezoid, the area of a trapezoid is the average height, so height 1 plus height 2 divided by 2 times the width. That's all it is. The average height times the width. So in this case, the average height, well, the height right here is 1. The height right there is 8 because, well, guess what? It's a y equals x. So 1 plus 8 divided by 2 times the width of this interval, which is a 7. That'll be 9 times 7, or 63 halves. So notice how quickly we start disseminating or pulling apart this definite integral into much easier computations. Times 63 halves plus 28. So I used a property of definite integrals to pull this apart. I used another property of integrals really to say the integral from 1 to 8 of 4 is just 8 minus 1, which is 7 times 4, which is 28. But honestly, I just think about things geometrically. The last one, which is the integral from 1 to 8 of x squared dx, that is not going to be something that we have a trick for. So that one we will have to use limits. So I'm going to say this piece, I'll highlight it here in yellow. This piece right here, we're going to have to use limits for. So I'll trade that out for the limit as n goes to infinity of the summation I equals 1 to n. And then I'm going to use the right endpoint rule, f of x sub I delta x. Okay, so right endpoint means that I'm using x sub I. Left endpoint would be x sub I minus 1. The rest of this stuff, I'm just going to go ahead. 2 goes into 4 twice. 2 times 63 is 126, so minus 126 plus 28. Let's go ahead and off to the right hand or left hand side, find out what delta x is. Well, it's b minus a over n, and b in this case is 8, a is 1, so it's 7 over n. And x sub I, using right endpoints there, is going to be a plus I delta x, or in other words, 1 plus I times 7 over n. So let me go ahead and replace that in that summation. That's the limit as n goes to infinity of the summation I equals 1 to n of f evaluated at x sub I, which is 1 plus 7i over n, times delta x, which again was 7 over n. This is all within this limit, so I'll just box that up. Negative 26 plus 28 is a negative 98. That's right. Negative 98. And we still have to work on this limit. Now, limits of Riemann sums and finding what their values are finitely is often a challenge. But we can do it. As long as it's a polynomial of degree 3 or less, we could totally do it. And this one is a polynomial of degree 3 or less. So this is going to be the limit as n tends to infinity. This 7 over n, it's not affected by the index I. So I'm going to factor out that 7 over n out of the summation. The rest of it's kind of stuck in there because the rest does rely upon I equals 1 to n. And we have f evaluated at 1 plus 7i over n. What is f? F is x squared. So this is going to be 1 plus 7i over n squared. It's just whatever our x value is, that's this, squared. And then we still have that minus 98 sitting off back. Let's go ahead and square that out. That's the limit as n goes to infinity of 7 over n times the summation. Again, I equals 1 to n. This will be 1 plus 14i over n plus 49i squared over n squared. Double check that, but that is correct. Minus 98. And now we have properties of summations where we can break this summation apart into 3 different summations. So I'm going to go ahead and do that. So you can see that this is a combination of evaluating using the properties that we talked about in the previous video, which is just splitting apart integrals and stuff like that, and evaluating using limits. And eventually we can avoid this, but right now we cannot. So this is going to be the summation I equals 1 to n of 1 plus, I would write the summation of 14i over n, but the 14 does not depend upon I, nor does the n. So I'm going to factor those out front. 14 over n summation I equals 1 to n of I. which I will trade out in a moment, plus, again, 49 and n squared, they don't rely upon n, so I'm going to factor 49 over n squared out of this last summation, I equals 1 to n of I squared. And again, we still have a minus 98. Now, to remind ourselves of those summation formulas from the very first video in this series, we're going to need to use these guys right here. At least the one for summation of I and the summation of I squared, and then the summation of 1 at the top. Summation of C is just C times n. So let's go ahead and do that. So equal the limit as n goes to infinity. We have the 7 over n that's just hanging out, getting ready to be used. Summing 1 to itself n times, that's going to turn into the n, plus 14 over n. The sum I equals 1 to n of I is n times n plus 1 over 2. Notice all my summations are beginning to disappear. We have 49 over n squared. The sum of I squared, that's the oddball of all of those summation formulas. It's going to be n times n plus 1 times 2n plus 1 over 6. And I've written that in there. And so that really cleans up all that summation stuff. We still have a minus 98 on the outside. Now I'm going to distribute that 7 over n through. So let's go ahead and do this, and then we'll take a limit. So I'll leave the limit here for the time being. And distributing through, I get 7 plus, let's see, 2 goes into 14 7 times. So I'll get 7, n cancels with n. But remember, we're bringing in n and 7 here. So we get a 49 in the numerator and an n plus 1 over an n. Let's see, what else can we do here? One of these powers of n, well, I'll just write it this way. 7 times 49 is 343. And we have n times n plus 1 times 2n plus 1 all over. And then bringing in that n from the denominator, we have n cubed times 6. But really, n cubed will cancel with one of those up. With that n upstairs, you'll have an n squared there. Minus 98. Double check my mathematics, but that is correct. And now we'll go ahead and maybe do a little extra manipulation. Since you're in Calc 1, it's probably a good idea for me just to do all the little calculations here. This is going to be 49 plus 49 over n. Right? If you distribute this 49 through, you get 49n plus 49. And n will go into those, so it'll give you 49 plus 49 over n. And then this guy right here, plus, I'm going to write this as 343 over 6 first. You should see that this is going to be an n plus 1, 2n plus 1 over n squared. If you divide both numerator and denominator by n squared, the denominator will not have an n squared, but the numerator will have, let's see, divide this by n, you have 1 plus 1 over n. Divide the other one by the other n that you were using, that'll be 2 plus 1 over n. And now you can take the limit as n goes to infinity. Anything with 1 over n's will tend to zeros. So in other words, this disappears, this tends to 0, and this tends to 0. And you get the following. 7 plus 49, which by the way is 56. So 56 plus 343 over 6 times 1 times 2, minus 98. And let's see what this comes out to be. So negative 42 plus 343 over 3. And 42 times 3 is 126. So that's going to be negative 126 plus 343 over 3. And 343 minus 126 is 217 thirds. 217 thirds. That's the area underneath that curve. Lots of work, right? Actually, most of the work was caused because we couldn't use geometry. That's a very important point to make. Most of the work within this problem was done on that integral, definite integral from 1 to 8 of x squared, because we could not use simple geometry to figure out what that area was. Everything else was pretty quick. We were actually done with everything else by the third line, but that silly x squared got in the way. So that's just a lesson here that you want to use geometry as much as possible. However, if you cannot use geometry, then it's going to be a little bit of work if you're using limits to evaluate definite integrals. If you happen to know tricks, just like when you started with Calc 1, if you had taken, let's say, calculus in high school and you knew some of the tricks, your teacher won't allow you to use them. You have to use limits. Same thing here. You have to use limits for right now when figuring out definite integrals. That's very important just for you to get used to them. Now let's start doing easier problems. So I went for the beginning, and then for the rest of this, I'm just kind of taking easy street. So given that for some reason, somebody tells us that the integral, the definite integral from 1 to 3 of e to the x is e to the third minus e. Let's just pretend that somebody tells us that. Okay, so that's the area underneath e to the x from x equals 1 to 3 is e cubed minus e. Use properties of integrals and this result to evaluate the integral from 1 to 3 of 2 e to the x minus 1. Well, the integral from 1 to 3 of 2 e to the x minus 1 dx. Properties of integrals tells us that we can break apart this stuff pretty quickly to 2 times the integral from 1 to 3 of e to the x dx minus the integral from 1 to 3 of dx, or 1 dx. You'll often see people write this as just integral from 1 to 3 of dx. I hated that when I was a student. I would always write a 1 in here. So you can if you want to. It doesn't really matter. It's the same thing, right? 1 times dx is the same thing as dx. But just letting you know. This is something I got I was so annoyed with in calculus. Now they tell us that this picture right here can be traded out for this stuff. So that's what I'm going to do in the next step here. That's 2 times e to the third minus e. But we still have this minus integral from 1 to 3 of dx. Always try to think geometrically. We're finding the area underneath the curve from 1 to 3, and the curve is y equals 1. So that should be a fairly easy area to find. Height 1 width 2, 1 times 2 is 2. So this is going to be 2 e cubed minus e minus 2. And you could technically factor a 2 out of everything, and that's an e cubed minus e minus 1. There you go. That is the area underneath this curve. And it's often, again, easy for students to begin to forget that they're actually finding areas. But that's exactly what we found. The area underneath 2 e to the x minus 1. That is the actual exact area underneath that curve. Pretty neat. Let's try another one here. Write the following as a single integral. First thing I'm going to draw your attention to is that all the functions are the same. So whatever curve it is, we're dealing with the same curve throughout. There it is. And notice it goes from -4 all the way up to +3. Yes, there's a -1 and stuff like that, but the highest x value is 3. So we're going from x equals -4 to x equals +3. Or are we? Well, let's see. I want this first one, this first integral, definite integral right here. It's telling us find the area underneath this curve from -4 all the way up to +2. So maybe right to there. Okay. Great. All right, I found that so far. And then the next one says, hey, by the way, add on to that the area underneath the curve from 2 to 3. Oh, well, that's pretty easy. Right? Now I know what these two add up to. It's just going to be the integral from -4 to 3. Okay. But then they say, by the way, lose the area between -4 and -1. That is lose the area, all this area right here from -4 all the way up to, let's just pretend that's -1 right there. Lose that area. In other words, all we want to keep is this yellow highlighted area here. We want to lose everything else. So when you do this problem, that visual is super nice. A little bit of geometry there. This is just going to equal the area underneath f of x from x equals -1 to x equals +3. So that is using properties of integrals. Very cool way of doing a problem. All right, let's see what else we have in store. Let's go ahead and estimate the value of this definite integral. So this is one of those cases where when they say estimate the value, you could look at this all day long. If you don't know Calc 2, you're pretty much stuck on this. So what you want to do is find out what are the bounds for the function. Like how low does this function go and how high does this function go? All right, let's take a look at this function from x equals 0 to x equals 2. Well, let's see. Our function is 2x e to the negative x. We know at time 0, it goes through 0. And we can easily see at time 2, it goes through 4 e to the negative 2. I'd love to know if there's a different value or another maximum on this. So notice how I'm bringing in some previous calculus topics. Let's see if there's a maximum elsewhere. Again, this is just me finding on this closed interval from 0 to 2, the absolute maximums and the absolute minimums. To do that, you test the edge points, which is what we just did there. And now I'm going to see if there are critical points for this function. So taking the derivative of that function, f prime of x, it was 2x times e to the negative x. So the derivative of 2x is 2 e to the negative x plus 2x times the derivative of e to the negative x, which would give me a minus sign right here. And if you factor a 2 and an e to the negative x out, you're left with 1 minus x. That's it. So we know that this is only 0. It's always defined, but it's only 0 at 1. So x equals 1 is a critical number. I'll just write it that way. And let's find out what the value of the function is at 1. Remember, the function was 2x e to the negative x, right? So 2 times e to the negative first. And that would be basically like a 2/3. So let's see, how does that compare to 4 e to the negative 2? Turns out slightly larger. I just grabbed a calculator. It's not that I know that offhand, but 2 e to the negative first, there we go. It's a slightly larger. So I happen to know that my curve looks something like this on that interval. Okay, it's a smooth curve because it's a polynomial times an exponential. And I don't need no concavity. I just need to sketch it out. The whole reason why I'm doing that is because we have a property. The integral from a to b of f of x dx is always less than or equal to m times b minus a. It's always greater than or equal to m times b minus a, and less than or equal to a capital M times b minus a, where little m is the smallest value your function will ever take on that interval, and big M, so this is little m right here, and big M is the largest value your function will take on that interval. So let's go ahead and just substitute that in. Little m, again, the lowest value for our function on this interval is going to be 0. So we could say that our integral is from 0 to 2x e to the negative x dx is between 0 and the upper value, which is 2 e to the negative first, times, again, 2 minus 0 there. So the estimate for this integral is it's some number between 0 and 4 over e. Now that is actually a pretty broad level of values, or broad amount of values that it can be between. Totally get it. But that's the best we can do, honestly, in this situation. Some people might say, well, can't you say that your function, the area's greater than this? Nope, I can't, because we don't know how sizable that area right there is. So we just don't know. So it has to go from the lowest to the highest. You have to take the absolute minimum on the interval and the absolute maximum. Those are your little m's and big M's. This is one of those properties that I said is rarely used, but it's kind of cool to use it. Well, here we've used it.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.